Hello, community. Today we talk LLM as an AI operating system. Let's dive right into it. Now, LLMs are being now used more and more for chats, to augment chats, to be your artificial partner in chat. You can ask ChatGPT a lot of questions from education to financial advice. But the limited context length makes here a continuous chat challenging. You always start new after each session. So, global corporation, which operate here these global chat platforms, they need our help to improve their profits. And you might ask, so what systems are we talking about? We are talking about WhatsApp, about Facebook Messenger, Telegram, Signal, Discord. We are talking about Slack, Microsoft Team, Google Chat, Zoom Chat. And so you see, we're talking about companies. The market value I ask here, BART, as of today, Microsoft more than $2 trillion, Facebook 800 billion, Google close to $2 trillion. So they have a problem to increase their profit margin. So what to do? So what is the problem? We have to solve a problem of billions of users that are chatting today on their platform. And the problem is that the LLM systems should remember their user-specific conversation. I give you an example. You say, hey, ChatGPT or GPT-5, remember the nice guy I met 3 weeks ago? And now maybe GPT-5 goes back to your pictures you have taken 3 weeks ago, or remembers here exactly the conversation you had with GPT-5 and says, hey, sure, his name was Jack and you liked his smile. So you see here, information suddenly needs to be fed into an LLM system. And then the user might say, hey, GPT-5, you are the best. Now let me tell you what happened today. So you see, you want a continuous stream here of actual user-specific information to make your platform more attractive for user, and you can sell more ads or whatever you do. And if you look here specific here at the leader of the market here at the moment, you know that there's a computer operating system that is currently here the dominant desk operating system with a market share of 70%. And now let's just imagine, we are free to think, and let's say, hey, maybe this corporation is interested to do the same on another system, on an AI operating system, which could become hopefully the most popular AI operating system. And I know that you code in PyTorch and in TensorFlow, but think about a system integration operating system. This is what is here, what the corporations are fighting about. And I need here a little bit of help from J2Sense. And you see here when he's building his water-cooled PCs, and you have here the motherboard, and you have here the Ryzen CPU, and you have here the RAM and the GPU, and somewhere down there you have your M2 SSD. This is what we are talking about, the next step after the next evolution step. So let's have a look in detail. If you look at your computer, at my computer today, what we have a CPU, and on the CPU we have the cores, and then we have an L2 and an L1 and an L2 cache per core with Ryzen, for example. And then here on the system on a chip, we have the L3 cache that is accessible to multiple CPU cores. Then, next step is we have here RAM, random access memory, the short-term memory storage for the CPU. This is here the data for the CPU. And then, of course, you have somewhere here your M2 SSD, and either you run SATA or PCI, different protocols, but this is here the classical architecture. And what they have, and this is the important fact, they have a memory management system about memory tiering, and it's about the distribution of allocation among all memory tiers. So either L1 or L2 or L3 cache here on chip, system on chip, or you go to the RAM, or you go to an SSD, or you go wherever you want to go. So you have here memory management happening today in the operating system of your PC. And talking about memory, here a form would be in databases such as Redis, an in-memory key value open source database. Consumes a lot of memory, yes, of course. And now we have an approach here by UC Berkeley. They say, hey, we look at the PC and we try to copy the idea of the memory management of a PC. Can we transfer this to an AI? And they say, hey, we have now MemGPT. And they say, hey, you know what? LLMs are increasingly being used for continuous chats. What an insight. And the limited context length makes it really challenging for the user to stay on the chat and continue to chat. Interesting. And they say, hey, with our MemGPT, this system can now simulate here in the first development phase here virtual memory in the operating system to create unbounded LLM context. And you know, I love unlimited context about AI system. And they say, hey, with MemGPT, we demonstrate here in the first prototype that LLM can be taught to manage their own memory. This is the interesting thing, that suddenly we see what we do in a computer operating system and we say, hey, can we integrate this to the world of AI system, multi-agent system, multi-AI systems, and maybe the next evolution of a computer? So their idea is, they look at this and say, hey, our CPU is more or less an LLM, maybe connected visual language model. So we have language and vision data where we can operate with those data. Now we know that those systems, when they are pre-trained and fine-tuned, they have a limited token length of, 4,000 tokens, 32K tokens with the latest GPT-4, or if you go here with Claude 2, about 100,000 token. Think about this as here the L1, L2 cache on the core, on the specific core on this system. And then now comes the brilliant idea, and they say, and now we build something like compute RAM memory. And this is now where the CPU, if it's doing a lot of work, can, as in computers today, switch out some memory, then ask back memory, so that we do not have bottlenecks operating here on this system on a chip. Beautiful. And the LLM can dynamically manage here its own context through some specialized function calls. And you know function calls from GPT-4 months ago, allowing this LLM to move data between here the main context, let's say on chip, and some closely stored memory units. So you can swap information in and out, and exactly like you do in your PC. And this MemGPT here says, here, we need here some storage, and maybe on those storage, different memory management system. Simplest case, you have a simple database where the LLM tells us, hey, for some milliseconds, I need some storage here where I write to a database. I save this information and then I can read it back. This is MemGPT. If you switch to another perspective and you look at this from a graph-based perspective, you can see here the upcoming architecture here as a dynamically evolving graph, where the nodes of our graph here are more or less multiple elements of memory. And the edges signify the operation or the mathematical functions, the tensor operations that are allowed between those memory elements in a graph. So you see, the application then of graph theory and complex system science will open up a new window to analyze here this management system. Now, from the work here of Berkeley, A very easy example. Say, hello, says the system. I'm pleased to have finally a conversation for you. I'm Samantha, says Bart. I understand you are studying computer science. What is your interests? And the human user comes back and says, hey, speed, of course, is my interest, and the thrill and the adrenaline I have. And then the system gets in this information, but at the same time says, hey, warning, conversation history will soon its maximum length of 4,000 tokens, 32K token. So make sure to save important information from this conversation to your new memory, to your new RAM, before it is removed. And now the LLM, or MemGPT, has been trained to generate tokens to save specific content parts. And you have here a simple command, hey, working context append this in my RAM, for example. Here the key personality trait here is this person enjoys high-speed adrenaline rush activities. And since we have hallucinating, it says like Formula 1 racing, an intense gaming session on a computer like CSGO. So you see interesting effects that come together. But let's focus here on the paper. So what happened? The system decides to generate now tokens, and these tokens ignites an action, and this action is that here we have now a new entry in our very close memory, in our database that lives there, with the information, hey, this human enjoys high speed and adrenaline rush activities. So you see, easy. It stores here the most important fact of conversations. And since in RAM, I don't know, you have really a lot of RAM, no problem to have there also some huge databases. I give you here a very simple schematic diagram. Let's say we have an LLM that is combined with a vision language model. And remember, the LLMs, both, what a coincidence, have a maximum token length of 4K. They've been trained together, so they are now one system, or you can see this as a multi-AI system or a multi-processing AI system. Anyway, the input channel is only limited to 4K token length. In the next step, now this system has been trained on to generate very specific, memory-specific function calls. And this function call goes out and says, hey, I just learned something in a conversation. So I as an LLM, now I write to a very close memory, to a very close system database. So the LLM now writes down, as I just showed you, hey, this person likes to do this and does not like to do B, C, D. This is the same memory management like you have today on a CPU if the CPU swaps out specific information to RAM. And when it needs those information back, it imports it back from RAM. Now we do this on an AI operating system as Berkeley formulates it. Next step. We have now additional content here. And let's say now I come back the next day and I have my query to the system and I say, hey, do you remember the conversation yesterday? And there's a specific question that is left for me. So system says, okay, great. Goes, for example, here to RAG, to an external database somewhere, I don't know, in the US or somewhere in China, requests the data, feeds back the data. So we have a query, then we have all the additional external data that we get here for the grounding here of this task, RAG-based APIs. And now is the new part, because now the system remembers what it was talking with you about yesterday. So it looks up the photos you showed yesterday, or the language conversation you had with GPT-5 yesterday. And now it imports the part that are important from yesterday, given a specific query. So you see that the total length here is 4K. And you see here, all of this combined is not exceeding 4K. this is here exactly in a simplification, in a schema, how MemGPT works. And you see, the more information you read back, the smaller, of course, this amount of information is you can feed back. Now, if you go from 4K to what GPT-4 has today, 32K, or Claude with 100K, you have the problem in the middle. But you see that this is here a solution, if you want, if you extract here from this system database the fitting, the correct, the answer that is really providing here additional, now internal data from your last conversation. Great. Okay, another example. The system can learn. It simply overrides its database entry. If MemGPT says, hey, welcome back, hey, you like to see a movie, and you as a human say, hey, I don't like horror movies, well, it's Halloween is coming up, so this is the wrong example. I'm sorry. So I say, yes, I like horror movies, and I do not like romantic comedy. Then MemGPT says now, hey, I have stored in my database something else. So I now replace here an entry in my database. And here you have the knowledge of centuries of database management, where you simply have one string of information that you replace with another string of information. You override the data with the latest information in this conversation. So you see, it is rather easy. However, whenever this trigger is given that a replacement is necessary or some external information will be retrieved from the internet, or some information from the history of the chat will be retrieved, you have here to teach here MemGPT. You have to learn MemGPT here with a training data set, when, in what circumstances, and what topics it is necessary to get this additional information. And since we have here a GPT system, a MemGPT system, we need a training data set. And they have been so nice to make this available on Hugging Face datasets, MemGPT, here our multi-chat self-instruct dataset. And if you go there, Hugging Face, this is the address for you, and you look here at the very first dataset, you see here the personas in the sequence. You'd have then the complete dialogue between those two people. You have the metadata information. You have the previous dialogue, so you can go back and see. Then you have here some initial persona treats. Then you have the update information on persona 1, the update information on persona 2. That given you have continuous talks, a continuous debate here between a GPT system and a human. These are the updated information. Then you have some self-instruct dictionary. So you see, this is really some more complex data stream. And now you say, hey, who created this data stream? You know the answer. Anyway, the summary, very short summary. For continuous chat, now we have here a prototype of a system that is similar to some virtual memory in an operating system, a RAM state of system if you want, to create some unbounded LLM context. Now, in the press, or maybe in some YouTube channels you have heard, we have unlimited token length. Now you know this is not the case. Just the database, the LLM system writes to this database. The database can be huge. So unbounded context refers here to the size of the database the internal LLM has access to. Our LLM can write to this close by RAM, close memory with a database or whatever management system, and for example record its own history. And as I told you at the beginning, they can be taught to manage their own memory. This is what we see in the training data set, that the system will be developing here a new memory management system for AI. This is interesting, especially with multi-agent, multi-AI system. How the interplay of the management control flow, this is something I think will go on in the next half year, maybe up to a year, to find here a new memory management system. So you have an actual decision by the AI itself how to manage its memory, and you have some grounded reasoning from the training data by the AI when the AI decides to access specific memory tiers for specific functions given your specific task. Wait a second before we go here to the addendum. In my last video about the AI trends, I showed you here this one, where we have the reasoning dilemma between multiple AI system and multi-agent system. And the idea was now, hey, wait a second, if I attach here now this LLM specific memory functionality with function calls to remember this, to remember your conversation with a user, is this also here a database or can it be a vector store? This means, can it open up a new market segment for all these new venture capital based startup companies that are specialized here on vector store generation? Would this be their second opportunity to enter the AI market here? I currently believe no. Why? A vector store is more or less a transformer or a sentence transformer. If you want, in the easiest way, it's a BERT system or an S-BERT system. This is it. You have a similarity operation in this vector space. But is this necessary to build a vector space to have this functionality here? No. Because here what you want is that the LLM remembers who you are, what are your hobbies, what is your profession, what do you like to do, what you do not like to do. So you see here, this is not to find semantic similarities of millions of database entries or vector stores, but this is here simply to provide here general characteristic, general information. So I do not see here for vector store currently here this as a second possible entry into the AI system. Because second argument here, think about gaming. You have your CPU and you have your RAM. If you take the analogon with the personal computer. If you play a game, you have here your CPU at 100% and you have a lot of information here in the RAM available. Not here directly here in the L1, L2 or L3 cache. This distribution, how today gaming stores here and manages here all the visual information for the next scene in your game, their RAM is not a vector store, is not transformed into an embedding. They have a complete other system, memory system, and the simplest memory system I can think of is paging. So at the end of this video, I will tell or show you one information about paging. So therefore, I do not think here that this would be a methodology for vector stores to enter, given the specific characteristic in multi-chat systems that you do not search for similar data, but you search for or you need characteristic data. Back to the addendum. And as you know me, I have some addendums, some thoughts now at the end of this video. If you look at the development, let's look at Apple. And here's a YouTube from the Apple Keynote 2022. And you see here you have your M1 chip, no, the M2 chip. And you have here two huge memory chips, 24 gigabytes of unified memory. Those are here exactly what we are talking about here. Additional memory real close by. And you notice that in the M1 and M2 chip and the upcoming M3 chip, you have here a CPU integrated, you have here a GPU integrated, you have here a neural engine integrated. So it's not anymore in the near future like we see with J2 Sense that you have a CPU from Ryzen and you have separated RAM and you have separated GPU maybe from NVIDIA, but you see that a complete system integration I think this is the future that Apple is already currently implementing today. And you see this in the M1 chip and the M2 chip and the M2 Ultra chip, and you know this better than I do. These function calls are really, really important. So I make here a short information slide here that those systems like GPT-4, we can enable them to execute function calls. And this incorporation serves multiple objectives that could be of particular interest, especially for AI system development. This is about complex computations. You know, the generative AI models are typically limited to text-based outputs, if an LLM, and with the function call, you have maybe computation. You can return results. So you are not just a text generator. Data transformation, integrated data science, and data engineering task with the help of function calls, or the interactivity. Function calls enable a more interactive and dynamic experience for our LLMs. Instead of just a text-based reply, you can execute code snippets, manipulate the data in real time, or even interact with external databases. Or in the simplest agent case here, we have RAG-based APIs or just pure APIs. And of course, this function calling enables here GPT in interacting in a more complex multi-stage operation, as I just showed you here with this new memory close by. If you want to see a video about function calling here, half an hour. But interesting, in the study, Berkeley noticed it heavily depends on the system. What are the limitations of MemGPT? Now, at first, more or less, they tell us, hey, it works with GPT-4, full stop. So, to be precise, GPT function, fine-tuned models, rarely made syntactic or semantic errors, so almost perfect. With ChatGPT fine-tuned models who are cheaper given the token, they generated incorrect function calls, which is not so good. And if you go here to the open source, or Llama 2 is not really open source, but say Llama 2 70B, you have complete incorrect function calls and you have hallucinate functions outside of the provided function schema. So forget about this. So you see our, let's call it monster GPTs, our GPT-4s, they are able to do this. Talking about function schema to system message, this is interesting here. You're on the right hand side. I've typed you a function schema to calculate here simply the area either of a circle or of a square. You see here what is the schema of this particular function, input, output, what are the allowed values. So to be correct, this function schema represents a formal description how a particular function should be used. You have the function name, input parameter, the data types, and the output. And this is a machine-readable specification, of course. It's a JSON file. And then you have the system message conversion. This schema here is then converted into a system message that the model can understand. And during the fine-tuning process, and remember, we are still talking here about memory GPT, the fine-tuning of memory GPT, the model is trained to interpret the system messages, thereby learning the correct way to call the functions. And once the LLM model or VLM model has been fine-tuned and understands the function schema, it can then generate function calls that conform to the schema when prompted, like when and to what extent collect new memory data. You will see here, if you read the paper about a parser, if you're unfamiliar with a parser, this is the quality cleanup if you want. So the role of a parser, after a function call is generated by the LLM, a parser scans through the generated syntax to ensure it adheres to the correct programming standards. This could be as simple as checking that every open parenthesis is also closed, to more complex tasks like ensuring type safety or argument compatibility. Why is it necessary to have a parser here? Because even after fine-tuning here, it indicates that fine-tuning alone does not fully eliminate the risk of syntactic errors. you still have here your LLM that can hallucinate. So to have a better syntactic precision in your data, you still have to apply a parser. Great. So hence a parser is still required for a syntax verification as a safety net here. Great. And I think the last term I want to show you is paging. We are talking about operating system. We are talking about current memory management scheme in operating system that eliminate the need here for continuous storage of processes here. So for a flexible use of RAM. And over the years and decades, we have here some fixed size blocks we call pages, and they are then mapped to some physical blocks we are called frames. And if you're familiar with this, we have a key concept of page, frame, of page table, and page fault. And coming back here to the memory, you have your virtual memory, but in the physical memory, this is in our case of a PC analogon, the RAM. Here is where the pages are stored in frames when they are loaded. And the translation, the CPU generates the virtual addresses that are then translated into the physical addresses by our memory management unit using the already mentioned page table. So you see, we're here on the way to find here a new operating system, either for the integration in computer system, and maybe in the near future we will have here on our maybe laptop or desktop compute station not only the classical PC, but maybe we will have here AI chips. Maybe we will have here combined CPU and GPU chips like we have already here in the M1 to M3 chips by Apple. And the memory management that is going on between them will be an amazing area of research. So this here, the chip management structure, the memory management optimization on these complete systems are really at the forefront of research. Great. I think this is it for today. We had a look here at why we develop here this memory GPT, why this additional memory capability is really interesting for the development of our LLMs. And we had an outlook how in the future complete AI systems will have here a really integrated memory management system. Thank you for watching. Thank you for listening. I hope it was a little bit informative, and it would be great to see you in my next video.